Welcome to 6th lecture of Module 2, which is on mass transfer coefficients. In this lecture, we will discuss the interphase mass transfer. In the previous lecture, we have considered mass transfer theories, particularly the mass transfer coefficient in turbulent flow, and we have discussed the two important theories, the penetration theory and the surface renewal theory, and how to derive the correlations or the equations for these theories and to calculate the mass transfer coefficients. So far, we have discussed diffusion mass transfer in single phase. Or in a homogeneous medium. But most of the mass transfer operation in practice involve transport of one component to the other component between the phases, between two phases, and the phases are insoluble in nature. Suppose if we consider the removal of ammonia from byproduct coke oven gas by water, absorption in water. So, in this case ammonia diffuses from the gas bulk phase to the gas liquid interface, and then from gas liquid interface it is transported to the liquid bulk. And this is one of the example of interphase mass transfer. There are many other similar examples are available for gas liquid interface mass transfer. Like if we consider the removal of objectionable H2S or sulfur dioxide gases by alkaline solution, that is also a two phase system, gas and liquid system, and it is another example of interphase mass transfer. Then how can we calculate the rate of mass transfer in two phase system? So, in two phase system, how can we calculate mass transfer coefficient? Since the diffusion and mass transfer takes place in both the phases, gas phase and the liquid phase. So, we have to take into account the individual mass transfer coefficient separately. As we discussed in our module 1, the driving force for mass transfer mass transfer in two phase system not the concentration gradient. not the difference in concentration. The driving force is basically the departure from equilibrium, and equality of concentration in the two phases does not ensure equilibrium. Then what is the true driving force for mass transfer in case of equilibrium between the phases? When we say equilibrium between two phases, we say that no net movement or no net transfer of the solute among the phases. At equilibrium, the chemical potential of the solute among the phases are equal. So, the equality of the chemical potential will tell the equilibrium states, and that time there will be no net transfer of the solute among the phases. Now, let us consider a simple example how to calculate the equilibrium concentration. So, consider a simple tank which is partially filled with water and in which some amount of air and ammonia mixture is introduced. The vessel is closed. So, as soon as the air ammonia mixture comes in contact, ammonia will transfer, since it is soluble in water, from gas phase to the liquid. And simultaneously some ammonia will escape back into the gas, and this process of transfer from the gas to the liquid will continues. Among the phases. And they may not be at the same rate. So, at a time when the net rate of transfer net rate of transfer become equal, then we say that the process is in equilibrium. System is in equilibrium at that temperature and pressure. So, if we take a small sample from this, so liquid sample we can collect from here and gas sample we can collect from here, and we can analyze their concentration both in the gas phase and the liquid phase. So, we will get the partial pressure of ammonia in the gas phase and the corresponding mole fractions in the liquid phase is x NH3 star. So, this is the liquid phase concentration, equilibrium concentration, and it is the equilibrium partial pressure at this temperature and pressure. Now, if we inject some more ammonia into the system, then keeping temperature and pressure constant, then it will reach another equilibrium concentration. Again, we will obtain a set of P NH3 and X NH3 star, and if we plot them, is known as the equilibrium curve at that temperature and pressure. Say it is at 20 degrees centigrade. Similarly, if we change the temperature and do the similar experiments, we will obtain another set of equilibrium data. Say it is at 30 degrees centigrade and say it is at 40 degrees centigrade. So, this is the Y S star and this is liquid phase, or in terms of partial pressure and the liquid phase mole fractions we can define it. So, this is the equilibrium curve, typical equilibrium curve. We can see that the solubility of ammonia of particular gas decreases with increasing temperature. And the equilibrium curves becomes more steeper. Now, how to calculate number of independent state properties required to define the system? So, we can define the state of the system by Gibbs phase rule, which states that F is equal to C plus 2 minus beta. F is the number of independent state properties to define a system, state properties. C is the number of component and beta is the number of phases. Now, if we consider a binary system, oxygen and nitrogen mixture, gas liquid system. So, in this case the component is 2, number of phases beta is also 2. So, F is equal to C plus, that is 2 plus 2 minus 2 is equal to 2. So, the independent properties required to specify this system is 2. So, if we generally take the temperature, pressure and composition of the system as the independent variables state properties, then if we mention temperature and pressure, the composition is automatically fixed. Another important thing from the equilibrium curve can be drawn that if two phases are at equilibrium, there is no net transfer of solute among the phases. This does not mean that there is no transfer of solute among the phases, but the solute move from one phase to the other phase are in same rate, and we say that the dynamic equilibrium is reached. And third thing is that, as we said earlier also, the deviation from equilibrium is the driving force for mass transfer. System at equilibrium driving force is equal to 0. Now, to calculate the equilibrium data, we mainly depend on the experimental data. There are some attempts to calculate the equilibrium data theoretically. Two important laws of equilibrium relations between the phases are very important. Those are Raoult's law and the Henry's law. The Raoult's law is applicable for ideal gas, liquid or liquid system. And it is expressed as P A star is equal to X A into P A, where P A star is the equilibrium partial pressure exerted by the solute X A is the mole fractions of solute A in liquid, and P A is the vapor pressure of A component A at a given temperature. The solutions which we say the ideal solutions will have the following properties. The solute and the solvent, they should be similar size and intermolecular forces, similar size and intermolecular forces. Excess volume of mixing is equal to 0 and heat of mixing is 0. Heat of mixing is 0 for both solute and the solvent if they are in liquid phase. The Henry's law which states that, and this is applicable for non-ideal gas liquid systems. And the important form of Henry's law is that partial pressure, equilibrium partial pressure is equal to H x A. H is the Henry's law constant, and P star the equilibrium partial pressure of A, and x A is the mole fractions of the liquid. And then if we divide these equations by P T, P A star by P T, the total pressure is equal to H by P T x A. So, this is Y A star is equal to M x A, where M is equal to H by P T. P T is the total pressure. So, this is another form of Henry's law. Now, we will discuss the mass transfer between the phases. As we said, the majority of the industrial applications involve mass transfer between two phases or sometimes three phases as well. And the phases, they are immiscible in nature. If we consider a solute changing hands between gas and liquid. For example, removal of CO2 from flue gas using amine solution. Chlorine forms with water form bleaching solution. So, in this case, the absorption of a solute into the liquid or the desorption of a particular component from the liquid. When solute transfer from gas phase to the liquid phase, we call absorption, and when it transfer from solute we call it stripping or desorption. The concentration near the interface changes and the mass transfer takes place in 3 steps. Solute transport from gas bulk to gas liquid interface, then at the interface solute is absorbed at the gas liquid interface, and third, solute is transported to the liquid bulk. The transfer of step 1 and 3 occurs by turbulence of the fluid phase. The transfer of solute from the gas, suppose Y A bulk, and this is Y A I at the interfacial concentration, this is X A I and X A B. So, the driving force in the gas phase is Y A B minus Y A I, and in the liquid phase is X A I minus X A B. So, what does it mean this Y A I and X A I? These are the interfacial concentration. Physically, it means that Y A I is the interfacial concentration of A on the gas side, and X A I is on the liquid side. Generally, at the interface, mass transfer is assumed reached at equilibrium. So, there will be equilibrium between Y A I and X A I. So, we can write Y A I is a function of X A I. If it obeys Henry's law, then we can write Y A I is equal to m X A I. If the two phases are not in equilibrium, then how long it takes to reach equilibrium? To attain the equilibrium, it takes fraction of seconds. So, we call there is no resistance at the interface for mass transfer. At the interface. Can be a good assumptions. However, there are some exceptions in this case as well. As we said, resistance at the interface is negligible and resistance to mass transfer offered by the two phases in contact. This is how the Lewis and Whitman in 1924 they visualized the interface mass transfer among the phases. They said that two stagnant film exist on either side of the interface. And mass transfer occurs through these films in sequence. Third one, they said mass transfer within the film by molecular diffusion only bulk phases well mixed so beyond these films concentration in a phase is equal to the bulk concentration. Equilibrium exists at the interface no evidence of these films in reality. So, according to this Lewis and Whitman two-film theory, we can see that there is a liquid side film and this is gas side film. this is a delta G and this is a delta L liquid film, and this is the molecular flux suppose this is YAB bulk concentration, XAB this is the liquid bulk concentration, and this is XAI, this is YAI, and we call this is turbulent bulk, gas bulk, and this is turbulent liquid bulk. So, 3 steps of mass transfer. One is bulk gas phase to gas side interface, and it will cross gas film. Second, gas side interface to liquid side interface, it will cross interface, and third, liquid side interface to liquid bulk. So, it will cross liquid film. So, the concentration gradient in the liquid film is linear, but the true concentration driving force is parabolic in nature. The flux Na from the figure we can write Ky YAB minus YAI is equal to Kx XAI minus XAB, and YAI function of XAI. So, equilibrium exists, and from this we can obtain YAB minus YAI divided by XAB minus XAI is equal to minus Kx by Ky. So, if we plot in terms of driving force, suppose this is your equilibrium curve and this is the point P of XAB YAB, then this is XAB YAB bulk concentration, and this is the slope of the curve, which is minus Kx by Ky, this will give you the XAI and this will give you YAI. So, this is the driving force in gas phase and this is the driving force in liquid phase. And suppose this is Q, which is XAI YAI. Now, Na is equal to Ky YAB minus YAI is equal to Kx XAI minus XAB. If all these variables are available, then it is easy to calculate flux. By experiment, we can measure only the bulk concentrations, because the measurement of the interfacial concentration is very difficult. So, no devices are available to calculate the interfacial concentration. So, by experiment only possible to measure bulk concentration and very difficult to measure interfacial concentration. Because change of concentration at the interface is very large over a short distance. So, ordinary sampling device cannot sample from the interface. So, the above relation Na is not useful for mass transfer calculations. This means impractical theory. Since the theory is impractical to calculate the flux, this leads to obtain alternate method. So, the alternate method is based on bulk concentration. We know that equilibrium distribution is unique at a particular temperature and pressure. So, Y S star is in equilibrium with X A B. If we look into the previous equilibrium curve, suppose this is P, this is Q, and this is the Y A I, this is X A I, and this is X A B, and this is Y A B. So, this is Y A star, which is equilibrium with X A B. So, N A will be K Y, capital K Y, Y A B minus Y A star. K Y overall gas phase mass transfer coefficient. Similarly, X A star is in equilibrium with Y A B. So, this is in equilibrium with X A star. So, we can write N A is equal to K X, capital K X, X A star minus X A B. So, this is the overall driving force in the liquid phase, and this is the overall driving force, and this is also overall driving force in the liquid phase, and this is in the gas phase, X A B. So, K X is the overall liquid side mass transfer coefficient. In the next class, we will discuss how to correlate between the overall mass transfer coefficient capital K Y and capital K X, and between small k y, the individual mass transfer, small k x, individual mass transfer coefficient, and which is required to calculate the resistances between the phases. So, we will discuss in the next class. Thank you.